Welcome to today's presentation. Thank you for taking time out and being here today. Today, we will be looking at what is the VFD device and how is it work, what is the benefits of VFD device, how do we calculate energy saving, and how can it pay back itself. Okay. Common terms for this electronic device used in drive technology are VFD, known as variable frequency drive, adjustable frequency drive, or AC drive converter. With this device, you can control speed, torque, and direction of an AC motor at the same time. This block diagram illustrates a typical three-phase AC variable speed drive system with its main components. First, incoming AC voltage enters a bridge rectifier, which consists here of 6 diodes. In middle stage, the DC voltage has ripples. Therefore, a capacitor and filters have to smooth out the ripple. Now, the DC bus system can take its place. The filter DC bus voltage pass through the DC three-phase AC converter to ensure the efficient operation of the motor. The sine waves produced by each pair inverted switches are 120 degrees out of phase. The longer the switches are on, the higher the output voltage. This way you can control torque of this motor. And regarding the speed of the motor, by increasing the frequency of the output signal, you got a higher number of revolution. So let's move on and talk about the benefits of VFD device in a nutshell for now. Okay, what is the benefits of VFD? You can see here the 6 impressive benefits, and the first one is the energy saving. Variable frequency drives allow you to consume the less energy than other speed control techniques when load requirements are less than full speed. Okay? And when we take a look, the other benefits are the soft start, easy maintenance, thermal and mechanical stress. The single speed starting method starts motor suddenly, subjecting the motor to high starting torque and to current surges that are up to 10 times the full load current. Variable frequency drives, on the other hand, to slowly ramp the motor up to operating speed to lessen mechanical and electrical stress, reducing the maintenance and repair cost, and extending the life of the motor and driving eco. Soft starts or reduced voltage soft starts are also able to step a motor up slowly, but drives can be programmed to ramp up the motor much more slowly and smoothly, and can operate the motor at less than full speed to decrease wear and tear. Can also run a motor at specialized pattern to further minimize mechanical and electrical stress. Let me give you an example out of my topic. An S-curve pattern can be applied a conveyor application for smoother diesel or axle control, which reduce the backlash that can occur when the conveyor is accelerating or decelerating. All right. So, another benefit there, at the instant of energization, the lock motor is about 600% of full load running current. This heavy current then drops off slowly as the load breaks loose and the motors come up to speed, but cause unacceptable voltage sag on the power system, adversely affecting other loads. It can also cause the shock damage and long-term excessive wear on the motor. Using this starting method may force the utility to impose a limit on the size of motor you can use, since across the line, starting causes problem upstream into the utility system. The switching sort of suddenly starting and stopping creates stress on the motor insulation. What about another benefit? Low amp and the high power factor. Usually, we are looking for the high power factor because of the reactive power costs and the penalty for reactive usage. Some governments have regulation about the reactive power usage. Some of them no charge, some of them they charge the unit price or penalty. All right. So low power factor causes you use the high amp, which is not good for the copper wires, which are located in the electric motor. Let me try to explain that on the video. what happens when pull a muscle? There are made of thousands of vulnerable muscle fibers, and a full rupture is the worst, right? Every fiber in the muscle is torn. And when we look at the video, there's a body and it's walking. The body has a brain control all body activities, and they say to muscle, just use energy to walk. You don't need more power than this. What's going on? What's going to happen if you spend more power than enough? Let's try to do something together. Please take a pen or a pencil and write your sign or write your name, okay? When you write your name, then please try to write your name again, but hold pen tightly and tighten up your arm. It is not easy, right? Probably you spent longer time and your name looks not pretty anymore because the muscles wasn't optimized. You spent power more than enough, and you caused the mechanical stress on your arm, and probably your arm a little bit tired because you caused electrical stress on your muscle. That's why we need the artificial intelligence. Exactly same things happen to motor when we push, even we don't need that much power. However, the VFD device much braver than bring, because if the voltage change dangerously on the power system, VFD can protect the motor and you can replace the VFD device in an hour. Otherwise, the motor will burn out and the maintenance team is going to spend at least 6 hours to replace the motor during standby production. You're gonna lose 6 hours just for motor. Okay. Let's take a look at the VFD market all around the world. The global variable frequency drive market size is expecting to reach $33.10 billion by 2025. And what is the reason? Because the people know how to save money, and also stringent government regulations mandating the use of energy efficient device, along with increasing energy prices, are also encouraging development of VFD across the multiple market domains. Let's move to our study. Okay. We used the 2 electric motors and a VFD device. One of the motors is 15 kilowatt and other one is the 11 kilowatt with 11 kilowatt VFD device. I'm pretty sure you are asking same question, why these are different than each other. If you remember well, one of the benefits was low thermal and mechanical stress, right? So we can reduce our fan safety factor 20%, and of course I can use smaller fan and the motor same demand. Let me show you that on the technical data sheet. So there is a 2 fan selection for same requirement, but one of them 55 kilowatt with VFD device and other one 75 kilowatt without VFD for exactly same requirements. Let's take a look and compare values together. When we look at the left side, technical data sheet, it looks like the fan is good enough for our requirements even without the VFD. Okay, this is my my requirement, and this is the fan capacity. But nobody can take this risk under this condition because we are talking about aerodynamic, which is dependent on temperature, humidity, elevation, and many other variables. That's why we always need to use the safety factor. But there's something we should not forget. Maybe we cannot eliminate the safety factor, but we can reduce it. And how do we do it? We can do it with the VFD device because the device gives us ability to control motor even if temperature or humidity level change. Let's do selection together, and then I can show you the flexibility with the VFD device, okay? All right. There we go. Okay. This is the 90 kilowatt, 3000 RPM fan airflow and pressure chart without the VFD device. And Uh, okay. As you see, yes, as you see on the video, RPM is a constant value right here. That's why we have limited flexibility based on airflow value. But if we will have the VFD device, we will have so wider flexibility according to RPM value fluctuation. You see, I can do whatever I like. I can control my motor, I can control my fan, and when you look at right here, the consumed power, when you look at right here, the consumed power change, you see, based on my selection. When we look at the consumed power, as you see there, fan with the VFD value lower than fan without VFD, and also consumed power is the 72 kilowatt here. And maybe we can even select the 75 kilowatt fan instead of 90 kilowatt, right? So when we doing very easy calculation to see the energy saving, my saving will be 59,000 kilowatt per hour and 59,000 kilowatt in a year. I know that the money we are talking about here cannot even pass the La Casa del Papa series, but at least this is the legal gain, okay? Okay, we collected our study data according to differential pressure. We changed the load and recorded the generated value to analyze. At 100% load, difference is only 0.8 kilowatt because the VFD device just reduced the thermal and mechanical stress, which is depend on startup shock and ramp up period. We knew that the utility voltage is not stable. This fluctuation causes stress. However, when we reduce the load, the consumption gap getting wider, wider, and wider. Okay. And when we look at right here without VFD device, consumption is still same. There is no big changes. Okay, let's flashback very quick and go over it briefly. Okay, first one, the power factor increased by IGBT means insulated gate bipolar transistor, which is located end section of the VFD device. So we are able to use the utility power more efficient than before. And the second one, the fan service factor. We reduced mechanical and thermal stress, and this way we reduced fan service factor 20%. We got rid of some worries. And also our power consumption reduced accordingly. Okay. Let's take the constant parameter dynamic pressure and guide our VFD based on the hourly temperature and the humidity data. There is a 3 investigation were conducted. 110 Pascal dynamic pressure with the damper control and with VFD control, and with VFD and the pressure sensor control. The change in temperature and humidity of the air will affect the dynamic pressure. So this will affect our production capacity, right? And we are gonna still consume the electricity. So you see here on the chart, we present non-stop running fan consumption in a year. The fan speed controlled by damper system consumption is 97,000 kilowatt per year, and the fan speed controlled by VFD system consumption is 95,000 kilowatt per year, and the fan speed controlled by VFD with pressure sensor system consumption is 89,000 kilowatt. Okay. How do we calculate and produce this number? And let me touch briefly of the subject. We use the collected data to produce all year consumption value. As you see on the table, we have temperature and relative humidity values hourly for all year. Okay. Also, we know the motor performance at the measured temperature and the humidity values right there. So we can generate the energy consumption according to the specific volume of the air at each temperature and humidity values. Let's take a look at the calculation method at this temperature and humidity. The airflow is 13.78 meter per second and the RPM is 1498. If the temperature reduced from 28 Celsius to 10.96 and the humidity increased 31 to 63, air specific volume could be changed. Thus, dynamic pressure will change, but I don't want that happen because the value specify my production capacity and it has to be constant. A pressure sensor can make this value constant. It can communicate with the VFD device to guide motor speed. Okay, so as you see there, the RPM value is changing according to weather condition. And in addition to that, the power consumption changes according to RPM fluctuation. Here is the 11 kilowatt motors, and you see, I said that a little bit because actually there is too many raw calculation. We should do this kind of calculation to figure out of the benefits of the pressure sensor. Okay, there is almost 100 pages of calculation singles by single to figure out what is the consumed power. Okay, so when we compare the energy consumption based on the control methods, we can see the differences according to thermal and mechanical stress reduction. This reduction reflects on energy saving. So there is the fan damper control system consumption is 97,000 and the fan with VFD control by hard enter adjustment. We just enter the RPM value and just leave it like this. And the consumption will be 95,000 kilowatts per year. And the differences is 1,489 kilowatts per year. And we are just talking about the 11 kilowatt motors, okay? So usually we are using at least the 55 kilowatt or 75, 90 kilowatt and 110 kilowatt for high pressure fan, right? And the saving gonna be more than this. When the VFD had control by the pressure sensor, energy saving is increasing and it will be 8,105 kilowatt per year. Let's make this number much more meaningful. Okay, the carbon dioxide emission in this kilowatt is equal to carbon dioxide emission from 645 gallons of gasoline consumed and the carbon sequestrated by 7.5 acres of US forest in 1 year. One of our mission is to protect our world and we have to take care of the environment because we are getting production source from the environment, right? Such as wheat, corn, etc. Okay, so I just did the calculation to see how much I earn, the saving in the year, but you can do your own calculation based on your country utility price to just to figure out how much is it, okay? So my saving, my earning, I mean, my money, 8,000, sorry, let me click. All right, 7,659 Turkish lira in a year. Okay, I use the ABB, this is our partner. The ABB VFD device, the 11 kilowatt, and the cost is 6,500 Turkish lira plus the Vega pressure sensor, 1,262 Turkish lira, and the saving in a year, 7,659. Saving in a month will be 638 Turkish lira. So the VFD device can pay back itself in a year, and averagely the VFD device lifetime is 14 years, right? So you just need to spend 1 year the pay 1 year for the for this cost, then you still have 13 years to earn money and reduce your manufacturing cost. What will happen if we reduce production capacity and optimize the system? Okay, see, all right, let's just reduce our production capacity 20%. And you see here on the chart, we present non-stop running fan consumption in a year. And the fan speed controlled by the damper system consumption is 95,000 kilowatt per year. And the fan speed controlled by the VFD system consumption is 69,000 kilowatt per year. But if we're gonna have the pressure sensor also, the consumption is 64,000 kilowatt per year. When we look at the damper control and the VFD control system, there is a 27,000 kilowatt saving per year. Okay? And when we take a look the damper control and the VFD with the pressure sensor control system, there is 32,375 kilowatt saving per year. This is the huge number, and we just have 11 kilowatt motors now. The carbon dioxide emission in this kilowatt is equal to carbon dioxide emission from 2,576 gallons of the gasoline consumed, and the carbon sequestrated by almost 30 acres of US forests in 1 year. A saving in a year is 30,594 Turkish lira. And as I said before, you can do your own calculation based on your country utility prices, please. All right. So now the saving in a year, 30,000, and saving in a month, 2,549 Turkish lira. So that's why it can pay back itself in 3 months. All right, 3 months, and we still have 13 years plus 9 months to earn that amount of money. And if you remember, if you see there, 2,549, and the cost is just nothing when we compare both of them. Okay, how do we save that much energy? This is the law, all right? This is the fan law. The centrifugal fan running at a half speed consumes only 1/8 of the energy compared to one running at full speed. This is because the torque needed to run a fan is the square of the volume. For instance, reducing the fan speed to 80% only requires 64% of torque. Furthermore, to produce 64% of the torque only requires 51% of the power, as the power requirement is reduced in same way. Okay, as you see on the figure, recorded values speak themselves, right? Because look at the reduction right here, and we just double check our measurement with this formula, and we did the calculation. The numbers almost equal. See. So the VFD device and presentation is done, and thank you for listening. And again, taking time out to be here today. Thank you, Mr. Milan, again.
Thank you, Burak, for this interesting and presentation, which I hope everybody takes note of. And as Alapala, we are now ready to introduce this or to offer this VFDs on our fans.
Mm-hmm.
And also I take this opportunity to inform you that we are further carrying out our research and development on the further optimization of the pneumatic system in a mill. So besides just saving on the VFDs, we expect that there will be further savings also on energy consumption once we have optimized our pneumatic system.
Yes, exactly.
So we are working on this, and I would also like to inform you that we have a test mill now in Alapala, near our factory in Chorum. And this mill is a full commercial mill running. It has a capacity of 100 tons per day. And with a fully commercial operative mill, we believe that we can have better results in our R&D in an actual condition. So this is how some of the places where we are carrying out our research and development. Thank you again for joining this, participating in this webinar.
Yes.
And we hope to see you in our future webinar, which we will announce, and the topic. And of course, we have, as I mentioned earlier, we have many guest speakers to make these webinars interesting for you as the participants. We have time now for a few questions, so please, maybe have your questions.
Yes, if you have question, you can just.
And we will try to answer these questions as best to our ability now, considering the time. But otherwise, some of the answers might be detailed, and we would like to answer them to you by email. Thank you.
They can send questions on mail.
So if you have any question, just pop them in the QA feature.
There is one question from Nick. I cannot see anymore. I saw it earlier on, but I can't see it anymore. I think it was the cost of the, I might be wrong, but what I read was that the cost of the, you are asking, Nick, you are asking for the cost of the VFD? Is that correct?
Can you repeat your price per kilowatt on which the saving is calculated? One of the question from Niels.
Yeah, from Niels, yes.
Yes.
Pardon. So the price for what was it, Burak?
Let me show you. Okay, the price is here. Okay, the price per kilowatt in Turkey is 0.945 Turkish lira. Which the saving is calculated. Okay, so right here we calculate the saving, the VFD device with the pressure sensor. Now the pressure sensor just the measure and getting the real-time measurement. We call that the IoT data, and this algorithm can guide our VFD device, and this VFD device can control our motor RPM value, because as I show you right here, okay, when we just reduce one RPM, it's gonna be very good saving. You can see on your utility bill. But if you need a much detailed answer, as Mr. Milan said, you can just send an email, and or we can just chatting on Skype or somewhere, so we can discuss in everywhere, how you like.
And we would also like to hear from you what other topics you would like to hear for us to talk about. We'd like to make it more interactive with with the participants. I think it benefits us all.
I couldn't get your voice well, Milan.
You couldn't hear me? No, we welcome suggestions from the participants on further future topics,
yes,
which we will be happy, if possible, to prepare and present. And in the meantime, we await your questions. for us to answer. We have some questions. From Ashwin Kumar, we have a message from Mr. Hassan Duman, one of our sales representatives in Alapala, and Mr. Chaktai. Mr. Chaktai, for a 200-ton mill, automation price is, no, this is nothing to do with the VFD at the moment, all right? I think you're looking at, we need to look at the flow sheet, but Mr. Chaktai, this question you should ask our Mr. Burak directly. Mr. Ashwin Kumar, yes, we can reply to you by email the power you will save by using VFD on a 75 kilowatt blower motor for your brand. Mr. Burak will answer to you this question because it needs some calculation and it takes time. So please send us your email and we'll be happy to give you an answer. I think these are the only questions we have for now. Please, we'd be happy to answer your questions. You can also send them by email to us, and we'd be happy to answer them. And thank you again, all you participants, and we look forward to seeing you again in our next webinar, which we will announce, and the subject we will announce. Thank you again.